Welcome to the Breakthrough Broadcast, a podcast about innovative STEM solutions to real-world problems. From emerging technologies to practical research, Drew Reck explores how science, engineering, and bold thinking are shaping the future.
Picture this. A train silently glides along a track. Not on wheels, but floating just inches above the rails. There's no clatter, no friction, just smooth, almost effortless motion as it reaches speeds over 300 miles an hour. This isn't science fiction. It's the reality of magnetic levitation trains, or maglevs, a technology that's transforming how we think about transportation. Maglev trains don't rely on traditional wheels or engines. Instead, they use powerful magnets to lift the train off the track and propel it forward. This allows them to travel faster, smoother, and quieter than conventional trains. It's a perfect marriage of physics and mechanical engineering, using fundamental forces and cutting-edge design to overcome the limits of friction and gravity. Hi, I'm Drew, and today we're exploring how maglev trains work, breaking down the physics behind magnetic levitation, and exploring the engineering innovations that make these floating trains possible. We'll look at the two main types of maglev technology, the challenges engineers face in building and maintaining these systems, and what the future might hold for this exciting mode of travel. Whether you're fascinated by magnets, intrigued by high-speed travel, or curious about how science and engineering come together to solve real-world problems, this episode will take you on a journey through the science of floating speed. Magnetic levitation, or maglev, relies on fundamental electromagnetic forces to lift and propel trains without physical contact with the tracks. At its core, the phenomenon involves generating magnetic fields that create forces strong enough to counteract gravity and air resistance, allowing the train to float and move smoothly. Understanding this requires diving into how magnets interact and how these forces can be harnessed and controlled. Magnets produce magnetic fields, invisible regions around them where magnetic forces act. These fields exert forces on other magnets or magnetic materials in their vicinity. One of the most basic principles is that like magnetic poles repel each other, while opposite poles attract. This repulsion and attraction can be manipulated to create lift. For a maglev train, the idea is to arrange the magnets in such a way that the train is lifted off the guideway by repulsive forces, or pulled up by attractive forces, effectively suspending it in the air. Likewise, electromagnets create magnetic fields, but they can be turned on and off with electricity. These are the type of magnets that are usually used in trains. There are two primary methods to achieve this levitation: electromagnetic suspension, called EMS, and electrodynamic suspension, or EDS. Both use electromagnetism, but differ in their approach to levitation and stability. Electromagnetic suspension uses electromagnets connected to the train above the rails, but extended down under the rails so that they can pull train upward. By carefully controlling the amount of electricity going into these electromagnets, the system maintains a stable air gap, usually just a few millimeters, between the train and the track. Because these magnets are actively controlled, sensors constantly measure the distance and adjust the magnetic force used to keep the train levitated at the optimal height. This method essentially wraps the train around the rails. One challenge with EMS is that it is inherently unstable. Without the rapid adjustments, the train would crash into the track or fall off. Sophisticated feedback control systems are necessary to keep the levitation steady and safe. Electrodynamic suspension, by contrast, uses ultra-powerful magnets on board the train to create strong magnetic fields that induce currents, or electrify, conductive plates embedded in the rail system. Since the rails have electromagnets in them, these induced currents generate magnetic fields opposing those of the superconducting magnets in the train, causing a repulsive force that pushes the train away from the track. This repulsion lifts the train several centimeters or more above the guideway, eliminating physical contact. Simply put, there are magnets in the train and on the rails, and the repulsion between the two lifts the train. The biggest benefit of these EDS systems is that they are inherently stable at higher speeds because of the induced currents increasing with velocity, creating a stronger repulsive force as the train moves faster. However, EDS trains usually require wheels for low-speed operation because magnetic lift is insufficient at very low velocities. The levitation forces generated by either method must counteract the gravitational force pulling the train down. Given that the typical maglev train weighs hundreds of tons, the magnetic forces required are enormous and must be generated efficiently. This requires the use of strong electromagnets, and, in the case of EDS, their magnets must be cooled to temperatures lower than negative 240 degrees Fahrenheit to minimize electrical resistance and allow powerful magnetic fields to form without excessive energy loss. The propulsion of maglev trains is also fascinating and closely tied to electromagnetic principles. Instead of conventional engines, maglev trains use linear motors, essentially electric motors that directly produce motion along a straight path, rather than a rotating shaft like an axle on a car that requires excess energy to turn. The rail system contains coils energized sequentially to create a moving magnetic field which pulls or pushes the train along the track. By precisely controlling the timing and strength of the electromagnetic pulses, the train can accelerate smoothly and maintain high speeds with remarkable efficiency. This method eliminates mechanical contact, removing friction losses typical in wheels and axles. One key advantage of maglev technology is the near absence of rolling resistance and friction. Traditional trains must overcome friction between wheel and rails, as well as air resistance. Maglev trains, however, float above the track, drastically reducing friction. While air resistance remains a factor, streamlined aerodynamic designs minimize this effect. The result is a system capable of reaching speeds far beyond those of conventional trains, with less energy required per mile traveled. Stability is a critical issue in magnetic levitation systems. Any small disturbance can cause the train to shift or tilt. In EMS systems, rapid real-time control is essential, especially since the train is only a few millimeters from contact with the track. Sensors monitor the gap and adjust electromagnetic currents thousands of times per second to maintain balance. In EDS systems, like said previously, stability improves naturally at higher speeds. In addition to levitation and propulsion, magnetic braking is an elegant feature of maglev trains. Just like trains can use electromagnetic fields that move along the rails to accelerate, in the same way the system can generate a controlled opposing force, slowing the train without physical contact. Essentially, they make repelling forces in front of the train so that it pushes the train backwards slowly. This reduces mechanical wear and enhances safety by providing smooth, efficient deceleration. In summary, maglev trains are a remarkable application of electromagnetism and physics principles. They harness attraction and repulsion between magnetic fields to levitate massive vehicles, use linear motors for propulsion, and integrate advanced feedback control for stability. This intricate dance between forces allows maglev trains to operate at speeds and efficiencies impossible for traditional rail systems, promising a faster, quieter, and more sustainable future of transportation. While maglev trains promise incredible speed and smoothness, actually building them is far from simple. The technology faces a mix of engineering, economic, and environmental challenges, each of which has inspired innovative solutions. First, infrastructure costs. Maglev systems require specialized tracks, often called guideways, that are completely different from regular train rails. These must be built to extremely precise tolerances, since the magnets only work correctly if the gap between the train and the track is carefully maintained. Again, it can be as small as just millimeters. Building these guideways from scratch costs billions of dollars, far more than upgrading existing rail lines. The best method we have to alleviate this issue is the development of modular construction methods, where sections of guideway are pre-built in factories and assembled on site. This could speed up installation and reduce costs. There's also research into hybrid maglev systems that can run on both maglev guideways and conventional tracks, lowering the need for full system construction. This would make the development of the infrastructure much cheaper, because we will no longer need to build fresh tracks, but it is far from reality and may not be a solution we get to see. The second issue is high energy consumption. While maglev trains are much more efficient at high speeds than traditional trains, they require significant electricity to power the magnetic levitation and propulsion systems. Over long routes, especially in areas without renewable energy infrastructure, this can increase the carbon footprint. Good news is that we continue to have advances in superconducting magnets, so we can cut down on power usage because they can maintain strong magnetic fields with minimal energy loss. Integrating renewable power sources, such as solar panels along the guideway, could also help offset electricity demand, although this is only marginally more effective than just building solar panels or wind turbines somewhere else and transporting the energy along power lines. The third issue is safety and reliability. Since maglev trains operate at extreme speeds, any system failure could have severe consequences. The magnetic systems must remain stable in all weather conditions, including rain, snow, or high winds. Otherwise, safety will be a big issue. There is no real solution to this problem. The only thing we have is that modern maglev designs include multiple redundant systems. If one set of magnets fails, another immediately activates to keep the train levitating. The trains also have advanced sensors that continuously monitor the gap between the train and the guideway to make instant adjustments for stability and improve safety. Another interesting issue is that of public acceptance in political support. In many regions, people are hesitant to support maglev projects because of their high upfront costs and long construction timelines. Politicians often prefer infrastructure projects that can be completed within a single election cycle, and the general population prefers projects they will be able to see the benefits of immediately. Projects like this will struggle to be funded, and will struggle to retain funding during the long and expensive construction process. However, some countries are introducing short demonstration lines to prove the technology's reliability and benefits. Once the public can actually ride a maglev train and see its advantages, support tends to increase. Finally, the large land use and environmental concerns are also an issue. Maglev guideways need long, straight stretches of land, which can be difficult to secure in urban or environmentally sensitive areas. In some cases, building them might require clearing forests, farmland, or protected habitats that would cause problems to many people. To resolve this, engineers are designing elevated guideways that take up less ground space and can be built over existing roads or rail corridors. These designs reduce environmental disruption and can blend more easily into urban landscapes. In short, while maglev technology faces significant hurdles, the solutions being tested show that most challenges are not deal breakers. The real test will be whether governments and private companies are willing to invest in these solutions on a large scale. The good news is that these technologies are being implemented in the real world. Several countries have built maglev lines, and some have been running for years, carrying passengers at incredible speeds. Take China's Shanghai maglev, for example. It opened back in 2004 and runs between the city's downtown and the airport. It covers about 18 miles in just 7 minutes, reaching speeds up to 268 miles an hour. That's faster than a lot of commercial planes during takeoff. But it wasn't an easy ride getting there. The line cost about $1.2 billion to build, which is pretty steep for such a short route. Plus, they hit some resistance when trying to extend it further into the city. People were worried about safety, especially electromagnetic radiation, even though studies showed it's safe. And of course, the cost was a big sticking point for officials. So while it's super fast and smooth, it's a rather niche line rather than a full network. Japan's been pushing maglev technology for decades too, and they're really going all in with what's called the SC maglev. They've been testing it since the 90s on a dedicated track in the mountains outside Tokyo. The trains have hit speeds of over 370 miles an hour in tests. The plan is to eventually connect Tokyo across the country to Osaka with this system, cutting travel time dramatically. But it's not a simple build. Most on the route will run underground, which means tons of expensive tunneling through tough terrain. They're also dealing with environmental concerns, like how it might affect the local water supplies. And the price tag? Over $50 billion just for the first leg. So while it's super promising, it's also a massive project that's still years away from full operation. Not all maglev lines are about breaking speed records, though. Japan's Limano line, for example, opened in 2005 for an expo and runs at much lower speed, around 62 miles an hour, designed for more local urban travel. It's quieter and smoother than traditional trains, but after the expo ended, fewer people used it. That shows a challenge for maglev in cities. It's great tech, but if you don't have enough passengers, it's hard to justify the high costs compared to regular subways or buses. South Korea also jumped on the maglev train bandwagon with a line that takes passengers to and from one of their biggest airports. It's a short, low-speed route opened in 2016, which means that it's quiet and eco-friendly, but it's pretty limited in reach and doesn't connect well with Seoul's bigger transit network. So again, ridership has been an issue. Germany actually pioneered a lot of maglev tech, starting all the way back in the 70s with their Transrapid system. They tested it extensively and had plans for real passenger lines, even hitting speeds over 300 miles an hour in trials. But costs and political hurdles stalled those projects. By the mid-2000s, Germany canceled almost all of their plans. The tech they developed didn't go to waste, though. It became the basis for the Shanghai maglev system. What these examples show is that maglev trains really work, and they can be incredible. But building them isn't cheap or easy. They need massive investment, political will, and smart planning to fit into existing transit systems. The countries that have made the most progress tend to have strong government backing and a long-term vision for the infrastructure. Smaller lines, like those in Japan and South Korea, prove maglev can work for local transit, but only if there's enough demand to cover the costs. So maglev trains are no longer just dreams. They're here. The big question is where and how quickly they'll spread next. Looking ahead, the future of maglev trains is both exciting and a bit uncertain. We know the technology works. It's fast, smooth, and efficient, but scaling up to a global level is still a big challenge. One area that's getting a lot of attention is making maglev more affordable and adaptable. Right now, building new maglev tracks is super expensive, and that's a huge barrier. Engineers are exploring new materials that could lower costs, like cheaper superconductors that don't need to be cooled quite as much. If they succeed, it could make maglev trains easier to build and maintain. One benefit of this is that it would mean that the trains wouldn't require as much ridership to stay operational and pay the costs of maintenance. There's also a lot of interest in combining maglev with other emerging transport ideas. For example, some researchers are looking at hybrid systems that blend maglev with things called hyperloops. What this would do is put maglev technology inside near vacuum tubes, which means there would be no air, and therefore no air resistance slowing down the trains. This could push speeds even higher while cutting energy use. It's still experimental, but it shows how maglev could evolve beyond what we think of it now. Another big trend is automation and smart control systems. Advanced AI could make maglev trains safer and more efficient by constantly adjusting magnetic forces, monitoring track conditions, and optimizing energy use. That means smoother rides and less downtime for repairs. On the infrastructure side, some countries are planning new maglev lines or expansions. Japan's working on extending its SC maglev line, aiming to open the Tokyo-Nagoya route in the next decade. China, despite its initial hesitation, has talked about adding more maglev lines connecting major cities. Europe and the US have several proposals on the table, but none are moving as fast, often because of costs and regulatory hurdles. And then there's the environmental angle. Maglev trains already produce fewer emissions than planes or cars, especially powered by renewable energy. As the world pushes harder for green transport, maglev could play a bigger role in reducing carbon footprints, especially for busy inner-city routes. So while the maglev future isn't guaranteed, the combination of new materials, smarter technology, and environmental urgency make it a very promising field. If some of these innovations pan out, we could see maglev trains becoming a much more common and game-changing part of how we travel in the coming decades. So there you have it. Magnetic levitation trains are no longer just a futuristic idea. They're real, running right now in places like Shanghai and Japan, moving passengers faster and smoother than traditional trains. We've looked at the incredible physics that make them float, the engineering challenges involved, and how countries around the world are taking different approaches to bring this technology to life. The road hasn't been easy. Building maglev systems take massive investment, careful planning, and overcoming environmental and political hurdles. But the potential benefits, speed, efficiency, reduced friction, and a greener footprint are huge. As new materials, smarter controls, and hybrid technologies develop, maglev trains might become a more common part of how we get around, especially as we look for sustainable solutions to growing transportation demands. Whether it's cutting down long commutes, connecting cities faster, or even inspiring new ways to travel, maglev technology offers a glimpse into a future where we're not limited by wheels or rails in the traditional sense. It's a field where physics, engineering, and innovation come together to push the boundaries of what's possible.
Thanks for tuning in to the Breakthrough broadcast. If today's conversation sparked a new idea, share the episode and follow the show wherever you listen. Got a question, idea, or breakthrough of your own? Reach out at breakthroughbroadcastconnect@gmail.com. Until next time, keep questioning, keep building, and don't wait for the future. Help create it.